So we focused on, one trajectory of the system, one state. So now we want to broaden our scope. We want to see what happens to a neighborhood. I don't know. Our eventual goal is to classify all possible motions of a given dynamical system and describe how important relative to other motions is any particular motion. To do this, we have to broaden the scope from just one point moving. And as you'll pretty soon realize, this just looks like some discussion, but actually it's very fundamental. By going from studying what happens to one initial state to studying what happens to a distribution in initial states, we're doing something very physical, which is to say that we never know any state with infinite precision. Mathematicians might know it sometimes, but in science, applied dynamical systems, there's always some uncertainty about initial states. There's also uncertainty about laws of nature. We pretend that Newton's law is immutable, eternal, etc., but it's not quite true. We know that all our laws are approximate and, good approximation, certain level of approximation. So now a weird thing that will happen in this course, which I don't really understand, we will only say that we don't understand the certainty in the states we are measuring, but we'll pretend that the laws are immutable. So we won't have to smear the laws, take a distribution of laws. And for some reason that works. So, I'm not sure why, but it works. Toward the end of the course, we might even smear out the laws and show that in the limit of determinism this works. Now, if you understand this and a few things will happen in this course, you will understand foundations of statistical mechanics. Because so far we have taken a state space and we have fibered it in a fiber bundle of trajectories, Lagrangian spaghetti. And every spaghetti has, you take a point on it, just a label. It says, this is 17 spaghetti. This is what it is at time t0 or something. But it's really only a label. The object is the whole invariant orbit. And that orbit has past and future. So, a great puzzle of determinism is why is it if you know everything about past and future, we cannot see future as in a mirror of the past. Why is it that we can go back and forth? The moment you start talking about neighborhoods, you'll realize in very simple dynamical systems, you will understand that you cannot go back. You can go back for finite time. It's called Lyapunov time or something, and you cannot go beyond Lyapunov time. And you just can't do it. And the reason why you can't do it is the same why you can't beat the housing bubble, the stock market, etc. Exponential growth is unsustainable. And what's very typical of dynamical systems is that all the errors generically tend to grow exponentially. That means in finite time, no matter how many computers you have, you won't be able to predict. And you will never be able to predict weather beyond, let's say, 10 days, no matter how accurate your measurements are. Just because it's intrinsic even to 3 degrees of freedom and not 10 to 24 like we think in statistical mechanics or some such number. So this is going to be all totally innocent, but it's actually a fundamental shift. So what we have in mind is we are in our big state space of infinitely many states, and we take a neighborhood, and you can think of it as the neighborhood defined by the fact that your initial state in your experiment is prepared by accuracy to 1% or something. You can think of it as some Gaussian, and you have points in this neighborhood. And the one we have studied so far is at the center of the neighborhood. So there was x0, our initial, the label of the Lagrangian trajectory, or our initial point. And then we went someplace in time, and we arrived to xt sometime later. But now we will sprinkle the neighborhood with a whole flock, a swarm of neighbors. And what's specific to determinism is that none of these spaghetti will ever cross any other spaghetti. They're all unique. So they will all go, and they'll do something. So there'll be somebody here doing this, somebody here doing that, somebody here doing something else. And at time t, the whole neighborhood, if you just smear it out and look at it as a picture, will be something. They look quite different than what you started with, because it turns that no linear flow deforms neighborhoods. It depends where you are in a state space, how you move. And the neighborhood, even a very small one, after some finite time sufficiently large, will be visibly distorted neighborhood. To describe what happens in a neighborhood, you can take another point, which is delta x at time 0 away. So here is a neighbor, any generic neighbor, x of 0 plus delta x of 0. And the time t later, this difference vector delta x will change. So this point will now be x, the motion of the center of the neighborhood plus delta x time t0. And now we make an assumption, which is, a good assumption for most physical applications, and there might be some set of exceptions which you treat specially, but most of the time this is good enough. We assume that this flow is differentiable, smooth and differentiable. We'll only use it as differentiable once, but in our mind we think it's, a smooth flow, C infinity flow, if you wish, infinitely differentiable. Then we can think of, what happens finite time t. And we'll do it in 2 steps. And for some reason, people get confused all the time in literature between these 2 steps. The first one is, this is a Lagrangian picture, but we also have Eulerian pictures. We have our equations of motion. So, when I look here, I have a velocity field that's tangent. So this tells me how I'll proceed. This is the vector field that defines dynamics in infinitesimal version of it, Eulerian version. So I can ask myself, what are my equations of motions for the neighbor? And V of this guy here, xt plus delta xt, by assuming that this vector field is smooth, you have Newtonian potential, so accelerations and velocities derived by differentiating in once, that's velocity, generalized velocity. So I can write this as V at the center of the neighborhood plus the first term in Taylor expansion. So let me say this is ith component in d dimensions. So this is, has d numbers, real numbers specifying it. And then times delta x j, both of them evaluated at that instant in time, wherever you are, right here. And this is a matrix very tasteful. So this is now the time derivative of what happens at that point here. So this is plus delta x at that point in time. So how does this vector vary in time? Approximated by the linear term. So neglecting other terms in the expansion. Then, this cancels out. And we get that delta of x of t satisfies a linear differential equation. So I'll write it this way: ith component matrix ij evaluated at x of t times the vector at that point. So this is now a linear differential equation for how this vector changes in time. And this matrix is very important to us. So, and since Newton, everybody invents nonlinear dynamics once a month in every application. So in 19th century, it was a common subject to mathematicians and theoretical physicists. There was no distinction between the two fields. And in first 3 quarters of 20th century, it was domain of mathematicians, so they made it totally unintelligible. And then in last quarter of last century, other scientists and engineers discovered that if they use computer, they can understand this stuff that's been codified mathematician. So they always, everybody invents a new word for obvious object. So this is a totally central object. This is a rate of instantaneous shear of the neighborhood. It was probably introduced by Cauchy in his theories of continuum mechanics for 3-dimensional bodies, but it's true in d dimensions as well. So, and rate of constant is given by the matrix d ij. It tells you how the velocity in ith direction varies as you shear, as you move in the j direction in the neighborhood. And I've looked at literature, and they're called stability matrix. I have a long scholarly remark about it, and remarks at the end of this chapter, chapter 3 on stability. And I will be very grateful for any criticism, inputs, errors, corrections, what you don't understand. We'll set up some kind of chat site, see where that works, but we are not there yet. So it's called stability matrix, or if you want to be really more precise, you can call it matrix of velocity, remembering this is this generalized velocity. Any dynamical system is converted in a first order dynamical system where, xt is v of x, and it's autonomous. It just depends variable, but not on the time. So in d dimensions. So it's not, your bicycle's velocity. And it's definitely not a speed, which is magnitude of velocity. So matrix of velocity gradients. Now when you look at this object, its dimension is 1 over time. So it's some kind of rate. So it's a rate of shear. And one thing that it's not a Jacobian, which I'll define in a second. Jacobian matrix is if you are in your all coordinate systems at x0, and then Lagrangian flow puts you in the new local coordinate system, dx at time t, that's how Jacobian introduced Jacobian matrix. And the Jacobian is the determinant of this matrix, tells you how the volumes change when you do changes of coordinates and integrals. So this is Jacobian. Now the reason I say this, it's very embarrassing, but extremely good people who I endlessly respect call this Jacobian. And the reason why they do this is because, most mathematicians, at least applied mathematicians, etc., they're obsessed with epsilons. They like to see what happens if you have a solution and you go through bifurcation and epsilon round. So they write entire books beginning from start to the beginning. So they actually never see a Jacobian. In this book, in this course, we'll be always going finite or infinite time. So the important stuff for us will be Jacobians, which I'll explain next. Anyway, so that's a rate of instantaneous shear, and that's a central object of the theory. And notice, usually we are given the velocity field, we're given equations. So this is something we have. But this is not actually what we need. It'll turn out that what we need is to find out what has happened to neighborhood some finite, possibly very long time after. And having just this doesn't tell us that. This just tells us what happens at an instant in time. So the thing we really care about is finite time. And that will look, formula the formula looks like the same, but I will actually look at the map. I'll look at xt is a time forward mapping of my initial point, x0. So it's a segment of the spaghetti, or a trajectory from 0 to t. And I would like to know what happens at finite time. So now what I do is I look at something that almost looks the same, but it has very different meaning. And the two things are related to each other as integral and integrand, or as, function and a logarithm of the function. I mean, they're quite different. So now I look at, write x at finite time I write it as a finite map of this point, x 0 plus the initial displacement to find what the final displacement is. And all these things are d-dimensional vectors, this function as well. I again do Taylor expansion. Time forward map. Starting on this point. So you know, ith component of the vector, ith component of vector. This exchange with respect to jth component of the vector times the initial displacement 0 jth component summed over j equals 1 to d of all dimensions. And now it's this object that in linear approximation tells us how this is going to deform. And you know, in linear approximation, deformations cannot be too wild. So basically, you'll see if I start with a sphere, this will give me a ellipsoid, you know, turned around some distance. But that will be very good for us. So the Jacobian matrix of the flow, of the linearized flow, well, okay, of the flow, will denote J. And you know, this depends where I am. This is instantaneous in state space. This depends on where I started and how long I go. And I'm using this notation of putting t upstairs. As you'll see, there is some kind of exponentiation going on. So t, it looks like it's exponentiating something. But if you don't like it, you can also write this as Jacobian that depends on initial point and the time that has passed, or you can write it as Jacobian of the initial points. So varying those guys, 0d, and what happens time t later along the trajectory. Or, you know, whatever notation makes you happy. Now, because in our work, we will all the time use these guys, you know, I'll just give them this particular name. I find it more compact. Yeah, in applied math, you also find notation d of f, meaning derivatives of, etc. And then, you know, depending if you're taking course in differential equations or, you know, maybe this we'll call fundamental matrix. I don't find it very fundamental. I find, you know, use of fundamental very confusing, especially in physics. So I don't call it that. So anyway, so that's Jacobian matrix, and that's stability matrix. And now, given the equations of motion, we have this, but we want this. So what's the relation between the thing that we have and the thing that we want? Well, before I do this, let me just spend some time talking a little bit more about this Jacobian matrix, set up some notation which we'll use from now on for the rest of this subject. I got an equation that said that a neighbor at time t was just a multiplication by a matrix of the neighbor at time 0. So this is linear, and what we know about linear problem is that whenever we have a linear problem in some matrix, you immediately look at its eigenvalues and eigenvectors. That we know. So the moment you have a matrix, we presume, I'll show you how to compute it, we presume you have computed it, we know that J, and I'll be sloppy, should have T here and X0, etc. And if you write books on quantum mechanics, etc., then this thing might be called J of initial point, initial time, or you care about Green's functions, xt, t0, t1, time t later, or something. So, this can be decorated as many symbols as you need, but I'll be sloppy and try to minimize the number of symbols. But the moment I have a matrix visit, I get a set of eigenvalues of this matrix. I will always use capital lambda for them, and they are numbered. So there is a first one, second one, and there is a D of them. And it will turn out that the things that worry us most are the very large eigenvalues lambda, much larger than 1, because they will have a property that if you have some uncertainty here, they'll multiply by a large number. So there's a natural ordering of the eigenvalues when you're looking forward in time, and that is to compute them and then write them as a list such that lambda 1 is larger or equal to lambda 2, larger or equal to lambda 3. But then you think, this is matrix of real elements, and we know that when we compute eigenvalues of matrix of real elements, they're either real and complex. So we have to put the magnitude signs here. So this will always be a convention. Now, when you have a complex pair, they have the same magnitude, but they have complex conjugate phase. So that's why the equality signs are here. Also, if you have a symmetry, you might find out that because of symmetry, that from quantum mechanics, that you have degenerate subspaces, meaning that you might have a whole number of them which have the same magnitude. That's perfectly okay. And now, the matrix, each one of them has associated with it an eigenvector. And the meaning of the eigenvectors is that there's a natural basis that whenever I have finite time evolution, then I can choose coordinates originally to point along the eigenvectors of this matrix, and then dynamics becomes one-dimensional because on each eigenvector is just multiplication by the eigenvalue. So instead of doing something very complicated in this one coordinate system done from the eigenvector basis, I have simple dynamics. And one thing that you might not be used to is when you look at the definition of this matrix as being the matrix of derivatives, there's actually nothing that says that this matrix should be symmetric. Now, so far you have lived this happy life of unitary matrices, etc., where everything was self-adjoint, unitary, orthogonal. And that means that if I start here with orthogonal frame, this will move it, deform it, but it will remain an orthogonal frame. However, in dynamics, this never happens. This is, totally unlikely. So it's never true, with some set of exceptions or measure zero, presumably, that J is its transpose, or that in any sense J can be made into an orthogonal or unitary matrix. So this is never true. And this goes by the name non-normality. And it turns out it's extremely important feature of nonlinear dynamics that the right eigenvectors and left eigenvectors of this matrix are different. They're not orthogonal set within each other. They're only orthogonal from left and right eigenvectors. And this non-normality makes nonlinear dynamics much harder than quantum mechanics. So let's see, what else am I supposed to say? So now, once you have this, I just have one remark to make, which is when you think of these multipliers, you have to think of them differently in case of continuous mechanics, a continuous time than discrete time. So if you're, so how to plot them? Eigenvalues. If you have discrete time, n equals 1, 2, 3, if I'm just going forward in time, then the only object that I have is this matrix. I don't have that other object, the matrix of velocity gradients. That's intrinsic to continuous flow. I just have J. So when you want to tell me about some property of your trajectory, what you should do is you should write in the complex eigenvalue plane, you should look at the real part. If eigenvalue is real, then it's on this axis. But you also, with kind of 50-50 probability, can get complex pairs, because there's no reason why not to get them unless there's some, unless Riemann hypothesis at work, or you're looking at quantum mechanics or some magical thing happens. But usually both of them happen. And now the most important thing about these multipliers plotted in a complex plane is that there is a unit circle, which doesn't look like a circle. Okay. Unit circle. So this is 1, minus 1, minus I. And if something is on a unit circle, it means that that particular eigenvalue has magnitude 1, and that will be called marginal. Now, marginal eigenvalues, for generic matrix, you don't expect anything to be on any line, because that's a small set in a plane. So you don't expect to see marginal eigenvalues, but the moment you have some symmetry, this can happen. So they're extremely important, and they typically have to do with symmetries, as we all do. And they're very painful, it turns out, because you have to testing where something exponentially unstable or stable is very easy, but testing where something is marginal is very painful because I can spend a long time and not be sure it's marginal unless there is a reason why that should happen. So now if I get some eigenvalue outside, so let's see, my lambda 1 is, for example, real sitting here. That means that when I look at the dynamics here along the first axis, I'll find out that in that direction, as this moves around, in that direction, I will actually be stretching, and I'll be doing this multiplicatively by this multiplier. So that means that distances expand along those directions, having to do with this eigenvalues. And there could be a complex pairs, but the main thing is we care about the magnitude that to explain the. Or they could be inside, so they could be here, or maybe here, or maybe there. So all these guys are contracting. So when we say something is unstable, we will usually mean it in a linear fashion. And we'll say that this particular trajectory is unstable, meaning that it has some, in linear approximation, it has some eigendirections in which I go away at exponential rate. Or there could be other direction in which I keep getting pushed in because the multiplier, its magnitude is smaller than 1, and that will be called stable. So the main thing that we'll care about neighborhoods is to classify everybody in a neighborhood into directions which are unstable, where things blow up. That's what we really worry about, because if you want to control, let's say, heart or a magnetic levitation train, then we want it to be stable. So we don't want it to just go exponentially fast off the tracks. So those guys we have to control, so we really care about, and that's very important here. Then there'll be these guys who are marginal. Someplace there will be 1 in this set. And marginal ones will give us lots of pain, so we'll spend a number of lectures studying what symmetries do to dynamics, and that has all to do with marginality. And the contracting ones we don't really care about because they take care of themselves. So if I do perturbation in contracting direction, it'll just heal itself. And this is actually the reason that this subject, which was originally developed as a theory of ordinary differential equations, also works for partial differential equations. Partial differential equations are morally an infinite set of ordinary differential equations. So if you have something, some field you write in terms of Fourier modes, that's a set of ordinary differential equations. And if you can show that your system has 3 unstable directions and 17 million stable directions, 17 million stable directions will take care of themselves. We will only have to obsess about unstable ones. So that's why this theory can work for systems which are very large dimensional. The theory will develop. So it's implicit in this notion of stability. So now what happens if I have, this is for discrete time. For continuous time, this matrix by itself doesn't really mean very much because every epsilon in time it changes. It's not something I can really get a handle of. So what I have to draw is coordinate system in which I look at the rates of expansion and rates of contraction per unit time. In other words, whenever I have an eigenvalue lambda, ith eigenvalue, it's natural to write it as exponential of time times a rate of expansion. The real part, and because this is a complex number, then we also put the complex part. And it turns out that sometimes these things can have minus signs, but I'll ignore that. Let's just say that that's not true. So instead of looking at this complex number, I take its logarithm. That I can always do. And now I look in the complex stability exponents. So this will be called stability multiplier. These guys here, big lambdas. These guys will be called stability exponents. Just that. So that's a rate per unit time, because there is time and this is dimensionless. So these are stability exponents. And if you're looking, it's, maybe you wonder why I'm taking this logarithm, but I'll motivate it pretty soon. But basically, suppose that I have a system, mathematicians love those systems, so there are hyperbolic billiards, etc., in which I have a constant rate of expansion. It doesn't depend on position. Then what happens to two trajectories, their distance will grow exponentially with time. And that's a totally natural thing to do. So here you have a different thing to plot. You should plot real part of lambda, which you use a lot, so we give it a name for every multiplier. Instead of I look stability exponent. And if my multiplier is real, and there is 50% chance of that, then it doesn't have a complex part. And that means that it sits on this line. This is the imaginary part of lambda. I'll call that omega. Now, if it's positive, the exponent, that it means I'm unstable. So this is, unstable. So what that means is if I have a neighbor which is on my eigenvector, corresponding eigenvalue some distance away, as the time goes, they just shoot along on this eigenvector at the rate which is e t to the mu. So, or I could have a complex pairs. So I could have something like that. And because, complex pair conjugate to each other, there's just minus of that. And that's also unstable. So, this is the mu of I and this is the omega of I. Or I could have solutions that sit on this axis, they're purely imaginary. I could have solutions like that. So this is multiplier is corresponding to the solutions e to the I omega. So that thing is just rotating on a circle. when I perturb it, or ellipse or something, it's not going anyplace, it's not going away. So this axis is where all the neutral marginal eigenvalues, marginal exponent. Or they could sit, and for example in fluid dynamics, then there is an infinity of things like that. All of them are contracting because they're negative. Real part is negative. Because here we have that absolute value of lambda, which is written as e to the time passed times the mu. Mu is negative, so they all contract. So for flows, you should do these things, and you have seen them in quantum mechanics, because when they teach you resonances, they do the same thing in quantum mechanics. It's not so unusual, but so for the maps, you care about multipliers. For the flows, you care about exponents. Stability multiplier, stability exponents. So I don't know what the time is, so somebody will have to rein me in. What? 30 more minutes. Anyway, give me, 5-10 minute warning. 12:59. What is it now?
12:59.
12:59?
Yes.
Okay, good. If I wait a little, it'll be 1. Okay. So, you might not still have a good intuition what these complex pairs are, but basically this is like a frequency, and you can always define the period of rotation, which is 2 pi over omega I. So this is one period. And when you're doing your simulations, you will not be usually sitting in a complex space. You'll be sitting in real space. So whenever you have a complex pair, you will care about real and imaginary part of the eigenvectors. So whenever you have lambda I plus 1, two successive eigenvalues in your list of the same magnitude, being e to the time times mu plus I omega, e to the time minus I omega. Along with them, your mathematic or something will spew out two complex eigenvectors. And what you want to do with these complex eigenvectors, the ith and the next one, which is just the complex conjugate of the I plus 1, is a complex conjugate of this guy, this vector. You want to replace them by the real part of E I and two real part, imaginary part of eigenvectors. So you get a pair of vectors. So what they will define on your trajectory, they'll define a plane. This will be the real and this will be imaginary. They don't have to be orthogonal. Imaginary eigenvector 1. So whenever you have a complex behavior, that means that there is a plane associated with it, spanned by two eigenvectors, and in that plane, depending on the size, for example, if this is larger, this is positive, then what will happen is that if you start in any neighboring point to the trajectory, this time that neighboring point will go around. And when you write this explicitly, you just see it has a rotation matrix. They're just sines and cosines, two-dimensional rotation matrix. And the time t will come back to the same eigendirection So you'll have this period, and you know, depending on the size of this thing, you'll either spiral in or spiral out or move on a circle, 3 generic motions. So complex eigenvalues just have this meaning that when you do a perturbation, response is oscillatory. You know, the thing behaves like either overdamped oscillator, which means it just shrinks exponentially, or underdamped, which means it shrinks as an in-spiral, or the thing is a good oscillator, it just oscillates forever. That means it's marginal, or it explodes. So these complex guys are nothing special, they're just important part of the story. Now, in these lectures, I will skip Newtonian mechanics, but you know, you're more than free to read it. So from point of view of generalized dynamical systems theory, mechanics is, in nuisance, it's a special case. And it's a special case which has symplectic structure, which, you know it as Liouville volume preservation, but it's a little bit more fancy than that. You know, P's and Q's come in pairs, the momenta, etc. And in some sense, they're preserved by flow. That's called symplectic or canonical invariance. So then it's a special case, and because of that symmetry, you'll find out that there'll be quadruplets of eigenvalues, which are rarer than doublets. You know, so there'll be something that, and of course you have to study it because, you know, lots of good physics is in classical mechanics, and you can't do quantum mechanics without it. But as we're not going to do quantum mechanics, we'll focus on extended systems and on noisy systems. I will not cover it this time. So now, do we have any intuition about these things? So there are these two objects. Well, let me say a little bit of intuition we can get immediately. So when we do perturbations, so we have a trajectory. Here is this guy. You know, the center trajectory, it's doing this. X of t, in that instance, initial point. What the trajectory has, it has a tangent field, which is our velocity field. So this is velocity of x. At this point, you know, tangent velocity at this point. That's how we integrate this thing to solve where we are. And you know, at this point, it's pointing this way. X at t1, and so on. So there is actually one special vector. You know, we are constructing a basis, local basis. And it'll be co-moving basis. You know, it'll be something that will move dynamically with this frame. And there is one vector that's obviously special. We're always given this vector. So what does Jacobian do to this vector? Now, you know, we already have an intuition. If I make a perturbation in this direction, this means I've just taken 2 points on a trajectory. So what dynamics will do is just move these 2 points. It cannot reverse their order because, you know, one is before the other, so the second one is always trying to catch up with the first one. When, you know, velocity is small, they come very close, things slow down. When velocity gets larger, then the first one tries to run away. But basically, when I get back here, they're still on this trajectory. So intuitively, I know one of the eigenvectors of the Jacobian because I know that if I multiply this particular vector, I have to get velocity later. So I can do the algebra, it's very simple, but I'll just state the result. And it's in the book. So you can check yourself that this intuition is correct. So the velocity time t is just the velocity original time times the Jacobian times t. So one of the things is transported naturally by Jacobian. So that's one of the things the Jacobian does. It moves the neighborhood, but it respects the time direction, the evolution in time. That's not distorted in any serious way. And later on, we'll discover, this relation will give us what we mean by invariance in time, give us some marginal eigenvalue that we need. Now, next thing that we need to do is I need to tell you how to compute the Jacobian. I told you we had the stability matrix or the rate of shear, but we want to find the finite time shear, which is given by the Jacobian. So how do we do it? So what I love about being theoretical physicists is that, we are allowed to do whatever seems too opportune at given time. So sometimes we do quantum field theory, sometimes we do mechanics, sometimes we do networks, God knows what. And things that used to look very mysterious. When I was a student, they always tortured me with time-ordered integration. So evolution, quantum evolution was a time-ordered something. And I did the algebra, etc. It seemed to be just quantum mechanics. But no, it turns out this is just property of any linear system. So we'll see the time-ordered evolution where you can understand it because, you can visualize what's going on. This is not Hilbert space. This is just moving some piece of material along a line. And that is the essence of computing the Jacobian to figure it out. So there are two ways to do it. One is to write the differential equation. And so what we can do is we can look at what ddt. What's the rate of change of x dx at time t? See, the squeal will probably be deafening noise when I do. By the way, you're very quiet, and I really appreciate it. I'm not being interrupted, but you can ask me something if you want to. The world will not fall. But I realize it's a straightforward stuff. We have a formula for what the exit time is. Its initial condition, it doesn't depend on time, multiplied by this matrix, which is time dependent. So, so what is this thing? So there are probably simpler ways to argue it, but you can think of this time derivative for every matrix element as what it is time dt later over time t divided by delta tau, and then we'll take the limit. on the right-hand side multiplied by delta x0. On this side, it's delta x at time t plus delta t minus delta x at time t divided by delta t. So I just rewritten this Newton-Leibniz-like. But this one I can do my Taylor series. So I can write this as 1 over delta t times, and when I expand the first term, we cancel, so that'll be term proportional delta t, so I'll find delta x, delta ith component times a delta x dx dt times delta t. So this guy's cancels, and out of it comes a very simple equation which says that this is true for any initial x0. So I get dj at time t, delta t, is proportional to this matrix, sorry. And you know, if you believe this, you'll believe anything, but here we go. The final result is correct. If you do this correctly and don't mess it up, you find out that variation of this matrix J is actually given by the matrix of velocity gradients. So the way this instantaneous distortion rate shows up, it shows up in the instantaneous change of the Jacobian. And it's a linear equation. It depends on where you're on your trajectory. And now you can just put this on your computer and compute at the same go the thing that you, for example, did for a flare. So you integrate this equation in 3 dimensions. So this is d-dimensional. And then you have, okay, let's write this, d dt. And then you have d dt for every component of the Jacobian. You have the equation Gij, which is you multiply by this matrix evaluated at this place on the trajectory. So the Jacobian and this place of the trajectory. Having started at x0, and the initial condition is at the initial instant there is no distortion, so there is just 1. When I started the system at initial time, nothing happens. So that's d square equations. And for your Slare flow, you can do it because you know there'll be 3 plus 9, 12 equations, and you know your Mathematica or whatever you're using can handle probably 1,000 or something without thinking very much. That's it. So if I was of certain school of thought, I would now say mission accomplished. go home and tend my garden. I don't have to tell you anything. You now know how to compute stability. And yet, if you try to do it, it's going to kill you. And for example, Sean Ding here has been integrating this for 4 months already, and now he's the master. But it took 4 months to be able to actually integrate this equation. So it requires quite a bit of thought and lots of applied mathematics, lots of stuff. And why is that? This is a linear equation. This is usually totally innocent. This stability matrix is usually something that has finite elements in it because, you have some vector field and velocity doesn't go to infinity. And it's not allowed to go to zero because if it goes to zero, then you stop, then you're solving a different problem. You're at equilibrium. So this is, kind of normal. But this is a linear equation. So these elements, which are normal, will get exponentiated, because linear equation, in a way that requires some thought, JT is really just an integral of whatever is here. So it's, it's something like that. So, what I'm writing is not correct, but it's morally correct. It says that even though this matrix here of shears, instantaneous shears, is a bunch of reasonable numbers, T can be anything. So the elements of this matrix can get very big, arbitrarily big as time goes. They're all growing exponentially. Now, some of them are getting exponentially big. So the leading multiplier is maybe 10 to 103. But other ones are getting exponentially small. So the smallest multiplier is 10 to the minus 214. So suddenly your matrix, you need 300 digits of accuracy just to get 1 digit of accuracy on slowest eigenvalue because you're computing at the same time very huge and very small numbers. So it turns out nothing has been accomplished by writing this. The thinking only starts now. How do you compute it?
Can you fix the indices because I'm kind of confused?
Pavel would want me to fix the indices, and Pavel is absolutely correct. I have to repeat what you say there. Happy?
Yeah.
Yeah, okay. Thanks.
Yeah. Even there, it's like when you
It's wrong again?
enclose in a box, that's a clear.
Oh, that one. Aye. That one is criminal. But you guys believe anything, so who am I?
KJ.
Yeah. I can write anything I want. I mean, you'll be just... Actually, now I'm seeing many more videos that I ever wanted to see in my life, and so YouTube opens this stuff, and one of them is video below my video said English teacher discovers that he can tell the kids anything. Well, what happened at this point, the battery on the mic went out. So we can only surmise what the rest of the lecture is. The lecture is pointing to mission accomplished. It's a subtle hint to a former president of the United States. And the lecturer is saying that far from being accomplished, the mission only started. For example, one of the students in this class, Xiong Ding, has spent 4 months trying to learn how to compute this Jacobian and its eigenvalues. It requires quite a bit of thought. And now I have no recollection what this is about. But let's hang in there and see where we can narrate a little bit. So at this point, Let's see what happens. He's still talking. We have no idea what about. He's very perfectly happy talking, but we have no clue what he's talking about, the lecturer. I remain totally clueless. Okay, stop talking and do something. Something is gonna happen right now. The lecturer will talk about actuary rates. So actually, this lecture I can redo from the beginning. I will start because this is explaining how Jacobian is really a time-ordered product, time-ordered integral over the stability matrix or instantaneous shear rate. And this will be motivated by one-dimensional example, by a finite matrix example, and then written in detail. So nothing is lost from here on. So we stop.